Math is such a huge world with so many amazing things in it, and prime numbers are some of the prettiest things that we have discovered from math so far. They show the simple power of mathematics, or as we call it, pure power. For so many years, we've been solving complex problems, and now let's discover the mystery of simple numbers. There are two kinds of integers of numbers, prime numbers and composites. The broadest definition of a prime number is a natural or counting number greater than 1 that has only two factors, itself and 1. For example, 2, 3, 5, 7, 11, 13, 17, 19. You cannot divide them evenly except by 1 in themselves. Conversely, the number that can be obtained by multiplying two whole numbers other than 1 itself, such as 4, 6, 8, 9, 10, will be the composites. Attention! 1 is neither a prime number nor a composite. So here comes our questions. What is the pattern of the appearance of prime numbers, and how can we find out all the prime numbers? These puzzles lead us to find the prime number theorem. For example, we list all the integers in the growing spiral, and we highlight all the prime numbers. Then let's zoom out and see the picture. Now we can see the prime numbers are growing around the center and never seem to end. Imagine there's a tree in the center that is infinitely high, and there are leaves dropping from the tree. We can find a lot of leaves right under the tree and near the tree, but as we walk away from it, we find fewer and fewer leaves, though we always find them. This is exactly like the prime numbers. As we're looking at larger and larger integers, we always find more prime, but the number of primes gradually drops the further we look. By this, we can see the infinity of primes. In 300 BC, the famous mathematician Euclid first gave out the hypothesis that there is an infinite number of primes. The way that he proved it was brilliant. He used the knowledge that we just learned last semester, contradiction. He firstly supposed that there was a finite number of primes, so he multiplied all the prime numbers and added 1. Well, then this new number is going to be larger than the number before. However, if the original assumption is correct, so that this number after adding 1 cannot be a prime, or it'll be the largest prime number, so this number will be the composite, which is divisible by many numbers, and then he divided by every prime number that he used to construct this number, and then he found out there is always a remainder, 1. So it's not a composite. As we said before, there are only two kinds of integers except one, prime or composite. It wasn't a prime number, so the initial assumption was wrong, and there's no largest prime. This leads us back to the question before. How many prime numbers are there? We use pi of x be the number of primes less than or equal to x. For example, pi of 1 is equal to 0, because there is no prime number less or equal to 0. Pi of 2 is equal to 1, because we now have a prime number 2. Pi of 3 equal to 2, because we have a new number of 3. Pi of 4 is still equal to 2, because there are only two prime numbers under 4. Pi of 5 is equal to 3, because now we have a new additional prime number 5. Just like this, we have 3 prime numbers and pi is equal to 6. So 7 to 10, there are 4 prime numbers because we now have the new prime number 7. And then pi of 11 and 12 is 5, and just counting like this. The famous mathematician Gauss used his unbelievable patience to count the number of primes in a copious amount of numbers, even up to millions, 300 years ago. Now let's graph the number of primes on the vertical axis and the size of x on the horizontal axis. As we zoom out to see billions of numbers, you can see the picture never become a flat line. Then let's think about the density of primes. The prime density is a percentage of the prime number within a greater number. We can let the number of primes found divided by the size of x. In the first 100 integers, we found 25 primes, so the prime density is 25%. In the first 10,000 of integers, we found 1229 primes, so 12.29% of prime. In the first million integers, we found 7.84% of prime. And in the 100 million integers, we found 5.76% of prime. And this is what I talk about the appearance of primes is slowing down as we find larger size of x. Then we put the size of x on the x-axis and prime density on the y-axis and zoom out. Now we can actually see how does it slow down. Amazingly, we find that the prime density is related to the natural logarithm. We use y and x to write the function of natural logarithm. After we graph it, we find the way that it increases is similar to the way of prime density reduces. And now all we need to do is just invert the function. We use 1 divide the natural logarithm, and as we zoom out, we find the curve the prime density declines. Now let's compare the graph of prime density and natural logarithm. We see the green one is a natural logarithm and the red one is a prime density. As we zoom out, they approach each other. This is known as the asymptotic law of distribution of prime numbers. Now we have a function that can tell us number of primes without counting. The prime density over the size of x is approximately equal to 1 divided by natural logarithm of x. Now for example, let's plug in x as 100 trillion. Turns out the answer is about 3.1%. Compare this with the actual result, which is about 3.2%. There's only 0.1% off. So now we can use this formula to estimate the number of primes with the size of x. Let's put in the picture. The number of prime is the area under the curve of prime density. So we can know that the number of primes equals size times density. And we assume that the density is natural logarithm. So x divided by the natural logarithm. This is the prime number theorem. And now let's go back and compare the prime number theorem, which is blue, and the actual count of primes, which is shown by yellow. As we zoom out, these two lines will find an overlap when we go for infinity. Now let's do an example. We want to find out the number of primes less than 100 trillion. Plug in the numbers, we get 3.1 trillion primes. Compare this with a real number, which is 3.2 trillion. This is over 99.99% accurate. Okay, so now let's see what we get. The size of x, the prime density is 1 over natural logarithm of x, and the number of primes is x over natural logarithm of x. This is the prime number theorem. However, it's always an approximate number. In 1859, another great mathematician, Bernard Riemann, published his paper on the number of primes less than a given magnitude. He gave out the famous Riemann hypothesis. It had been listed as one of the 7 hardest math problems in the world. It was going to find the accurate value of prime number theorem. And as of right now, no one can solve it yet. After about another 40 years, in 1896, 2 young mathematicians, Hartmut and de Laval-Besson, finished proving the prime number theorem independently. They were the first group of humans who successfully finished this great topic. The prime number theorem is like an arrow. We used it to break through the limit of the world of human brain math. But there are millions of math problems like arrows that are waiting for us to shoot them into the sky full of stars. So let's just open our eyes, read, study in the universe of mathematics.